sir.
Is it visible, the board?
Yes, sir, visible.
Okay. So last time we were doing, we were analyzing the intrinsic semiconductors. Intrinsic semiconductor means semiconductors which are free of any impurity. There is no impurity, right? There are no defects. So those are intrinsic semiconductors, right? We tried to calculate to derive a formula for the intrinsic electron concentration. How do the concentration of electrons in the conduction band change with temperature or other parameters? How they change, right? How the concentration of hole changes, right? We wrote a formula for them, right? And last time for intrinsic uh, for intrinsic semiconductors, last time, right? We said that electron concentration in the conduction band, right? And remember, the zero meant that they are in equilibrium. There is no thermal gradient, there is no temperature difference between two different points in the semiconductor sample. There is no potential difference. So the semiconductor is considered to be in the state of equilibrium, which is represented by the zero sample. So N naught was equal to Nc, which we call it the effective density of states, right? E to the power minus Ec minus Ef over H, right? That was the concentration of electrons, right, in the conduction band when the semiconductor is in equilibrium. Ec is the conduction band bottom energy and Ef is the Fermi energy, right? What was Nc? Nc was equal to 2, right? And to 2 pi Mn star, where Mn is the effective mass of electrons, At divided by n squared 3 by 2. Right? That was the effective density of states. Remember, in my last lecture, I forgot to put in the density of states to put h square in the denominator. So I have put a comment on uh, my YouTube lecture that there is an h square or h cube divided the density of state should be divided by that h cube. There's a comment. So go to that comment back. And I will always again instruct you to please read my lecture in comparison with the book. I hope I have given everybody the book. So I hope and it should be that you will be reading the book. Right? So that is the effective density of space, and it is a function of temperature, right? And it is a function of the effective mass of the electrons, right? Now, also the whole concentration in the valence band was equal to N V and e to the power, right, EF minus EV divided by KT, right, where N V is equal to, right, 2 to 2 pi FP star KT for X squared. So this was the situation for intrinsic semiconductors which are free from any defect. There are no impurities in it, right? Okay, now we should see what is the position. Like, look, we said N naught is the number of electrons in the conduction band. P naught is the number of holes in the valence band, right? So how the electron concentration changes, right? This is also related with the Fermi level, the position of the Fermi level, right? Generally, we said the Fermi level should be in the middle, somewhere in the middle of the band gap. We define the Fermi level as the energy below which all the states are filled at t is equal to 0, right? And if you remember, we plotted or we drew that curve, the Fermi-Dirac probability occupation function, right? So at t is equal to 0, below that it was 1. And above that, above the Fermi level, it was 0. Then when the temperature is not equal to 0, it was kind of the middle, right? Now here, how does it change precisely with the effective mass and with temperature? With temperature, it should vary because these things are a function of temperature too, right? So let us find the position of the, right, intrinsic Fermi in position of the Fermi level in case of the intrinsic, right? Okay, now we say for the Fermi level, right? Look, this is an intrinsic semiconductor, so N naught must be equal to D naught because there are no impurities. So all the electrons that have moved to the conduction band, right? So all the electrons which have moved to the conduction band, they have left behind a hole there. So N1 is equal to P. So this is suppose equation number 1 and this is suppose equation number 2. So 1 is equal to 2. Equation 1 is equal to equation 2. So we get MC and e to the power minus EC minus EF over KT, right? That is equal to NV and e to the power minus EF minus EV over KT, right? Now, for mathematical simplification, let us take logarithm on the both sides, right? So when we take log on the both sides, right? Log of C, log of MC, right? Minus E C minus E F for KT, right? That is equal to log of NV minus, right? EF minus EV over KT, right? Okay. We can write this as just geometry plus minus simple algebra, and we will get EF is equal to, right, 1 over 2 and EC plus EV, EC plus EV, right, plus 1 over 2 is log of NV divided by X, right? Now put the value of NC NV and NC, right? These values. This is the value of NC, and this is the value of NV. So the power 3 by 2 will come in the front, right? So EF will be equal to 1 over 2 EC plus EV plus 3 by 2, right? Into KT log of M P star divided by Mn star. R, this is equal to, that is the mid gap energy, E mid gap. The mid gap energy plus 3 by 2 KT and log of, right? MP star divided by Mn star. So, in the case of intrinsic semiconductor, right? In the case of intrinsic semiconductors, the Fermi energy will go or can go above or slightly above the mid or below the mid. It can go to levels, it can move up or down the energy band. The Fermi level is equal to the middle, right? So look, that is the conduction band. That is the valence band, right? And as any temperature at T not equal to 0, yeah? At T is equal to 0, the Fermi level will be here, right? But at T not equal to 0, it is supposed to stay, right? So here, that is E med. We say at T is equal to some temperature. From that graph, the probability of occupation of the Fermi level is half. Right? So it lies here. The Fermi level lies here. I will not put the EF sign here because if the temperature increases, right? Temperature increases, the Fermi level will go a little up. If the temperature decreases, it will go a little down. It also depends upon the effective mass of holes and the effective mass of electrons. So it is a function of the temperature as well as it is a function of the effective mass of electrons and holes. The Fermi energy is a function of temperature as well as it is a function of effective mass of electrons and holes. Right? This was something related to the intrinsic Fermi level. Right? The intrinsic Fermi level. Now, our semiconductors are not intrinsic, right? We dope impurities into it so that to control their conductivity. Semiconductors are very useful material. They are better than the conductor. Why? They are better than the conductor. Why steel is not used in electronics? The conductivity of steel is very much high as compared to semiconductor. It is because we cannot use the we cannot control the conductivity in steel. We cannot control the conductivity in silver or gold or copper. But in semiconductors, we can control the conductivity. We can tailor the properties of a semiconductor. Therefore, semiconductors are very useful material. We can make them resistors, we can make them conductors, we can do whatever we want with it. Right? Therefore, semiconductors are very useful material and they have brought up a revolution. Okay, now we want to dope, we want to put some impurities into a semiconductor crystal. हम semiconductor को थोड़ा सा गंदा करते हैं, right? इसमें गंदगी डाल लेते हैं थोड़ा सा, semiconductor में थोड़ा सा गंदगी डाल लेते हैं और गन से it becomes very useful. The dirt makes a semiconductor a very useful material. So let us make the semiconductor a little dirty, right? Put some impurities, कुछ थोड़ा सा गन डाल देते हैं, and that is called extrinsic semiconductors. Semiconductors which contains some dirt, some gandagi, right? So extrinsic semiconductor. Extrinsic. Right? Extrinsic semiconductor. So, like a semiconductor is suppose made of silicon or germanium, right? Suppose semiconductor is silicon or germanium, a group 4 element, and suppose it's very pure, right? So there we can put either like aluminum in it, or we can put gallium in it. We can put an element from group 3, or we can put an element from group 5, right? So there will be kind of generally two types of impurities, right? Two type of impurities. So one we will call donor impurities, and acceptor impurities, right? Donor impurities and acceptor impurities, right? Suppose you have silicon, right? So it is like that. Silicon, 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 right? So it has a bonding with it, bonding with it, bonding with it, bonding with the neighbor, bonding with the neighbor, bonding, covalent bonding. What type of bonding in semiconductor? Covalent bonding, right? It has covalent bonding. So all these atoms are silicon. Suppose they are silicon, right? Now we put right a suppose we put an element from the group 5, right? We can put nitrogen, we can put arsenic, right? In in this silicon, right? Suppose we put arsenic in it, or antimony, or bismuth, or phosphorus, right? Suppose we put in it one of them, right? So it will be like, suppose I put an arsenic atom, right? So arsenic has a valency of 5, right? So it has 5 electrons in the outermost shell, right? So bond with this will be full, bond with the neighboring silicon will be full, bond with this silicon will be full, bond with this silicon will be full, and there will be an extra electron that will be kind of dangling. Because it will have smaller energy. A dangling electron which will not be bound. One electron which will not be bound in any bond with the neighboring silicon. Suppose this is arsenic, right? Okay. So what does it mean? This is tightly bound under a covalent bonding. 4 electrons are tightly bonded under covalent bonding. This is not very tightly bound to the nucleus of arsenic. It has, well, it needs a very small energy. That is about 25 MeV, like small energy. It needs a small energy, right, to break its bond with arsenic, right? And then it is free. It, when it breaks the bond, it is free. And free means it can respond to any external electric field. It can respond to any external electric field. You have an electric field, it will फौरन ये दौड़ दे, right? Because it is free, किसी का गुलाम नहीं है, right? So this small energy is equal to, by chance it is equal to room temperature energy. Room temperature energy is also So at room temperature, normally an intrinsic semiconductor will not be ionized because the bonds are very tight at normal temperature. But the dangling electron, like you have put impurity into the silicon crystal, right? So this can break with its parent nucleus, right? When this breaks, we said at room temperature. Because room temperature is usually, you can calculate this. Put T is equal to 300 Kelvin and put the value of the Boltzmann constant, and you will find out that the energy is equal to kind of 25 MeV, right? So this energy is sufficient to ionize an impurity atom. To ionize an impurity atom. This is an impurity atom. So to ionize it. So to ionize it means it is free and it is in the conduction. Right? So we can write the situation in an energy diagram. Energy band diagram. Energy band diagram. Right? We say there are, like from band theory of solids, we say there are bands. Right? That is the bottom of the conduction band, and that is the top of the valence band, right? Right? We said there cannot be any levels in this. States are not allowed. This is forbidden. जब तक कुर्सी नहीं पड़ेगा दे देंगे, right? So we said that the introduction of impurity in a pure silicon here, and that impurity is supposed pentavalent from group 5. So it introduces small energy levels close to the conduction band. Close to the conduction band. We call those levels as donor levels. Donors. They are close to the conduction band bottom, right? And we say this energy is the small energy, and which is equal to 25 mc. This is a small energy, and the room temperature is enough to make electrons take a transition from those donor states to the conduction band. Right? This is small energy. At this room temperature, which is room temperature energy, right? At this temperature, it is difficult for an electron to jump from here to here. But this is not that big a gap. So here, we call these levels as donor levels. Donor levels. Right? Because they can donate an electron to the conduction. So we call them donor levels, right? And we call these group 5 impurities. Now the conductivity increases. So at room temperature, you have good conductivity, right? And you have pentavalent impurities. आपने गन डाल दी है सेमीकंडक्टर में, प्योर सिलिका में, खालिद सिलिका में आपने गन डाली थोड़ी सी, और गन डालने से इसकी हालत और भी हमारे फायदे की होगी, राइट? हमारे फायदे का हो गया ना. We can control its conductivity. So we call that donor levels, and this impurity group 5 in silicon is a donor impurity. Right? This is called donor impurity and extended. These are extended semiconductors. Right? Now, Now, calculate acceptor impurities. Suppose we put gallium from group 3, right? Group 3 in silicon. Group 3 in silicon, right? For example, you put gallium in here. Gallium, right? So, suppose it will be one electron. There are 3 electrons in the final, in the last shell. So, there are 3 electrons. So, covalent bonding, what suppose it is completing covalent bond with this neighbor, and with this neighbor. But this with this silicon neighbor, the bond is incomplete. There's a hole. There is only one bond here, right? So now it's already a chair, a small chair. So an electron from the neighboring bond can hop to this, right? And there will be a bond, a broken bond created here, or we can say a hole will be created here. So this situation gives rise to conductivity in the valence band, or we say conductivity because of holes, right? Because hole can move, like electron from moving from here to here, then this electron moving from another electron moving to this state, which is empty. So we can say that electron can hop around from bond to bond. Or in other words, we see that the hole is moving. A hole is moving in the valence band. Similarly, this energy so that an electron can easily move from one bond to another in the acceptor situation when you have put already one chair. You have already put the chair here. Right here, it does not need any temperature to make an electron jump to the conduction band and a hole is created. No, a hole is kind of already there, right? Only slight energy to make the electron move from one to the other one. So this also luckily needs about 25 MeV energy. We say we say now the this arsenic, we say it is ionized now, or we say the ionization here in the donor situation energy, for the donor energy, the ionization energy is how much? It is 25 MeV, because the arsenic element is now ionized because the electron has jumped to the conduction band. Here in the acceptor impurities, electrons can now come and occupy this gallium atom. And now the gallium, we say it is ionized. It has a negative charge over it. It has a negative charge, right? So we say a hole is ionized, right? The level is ionized. So we can represent the same situation in an energy band diagram. If that is a conduction band, that is the valence band, right? So we say that adding group 3 impurity actually introduces small energy levels, allowed energy states close to the valence band, close to the valence band, and so that a hole can move. Look, actually, what happens when there is a small heat, that is room temperature? So electron will jump from here to here. Electron will jump. So when an electron jumps, right? So a positive hole will be created. And this level will get ionized. So here will be a negative charge. We call this ionization on hole, right? So a hole will be created. So ionization will be produced, positive charge and a negative charge. This ionization energy is again kind of 25 MeV, right? For the acceptor impurities. We call them as acceptor levels. We can call it EA. These are levels. We say an acceptor impurity introduces acceptor levels in the forbidden gap. Right? The introducing acceptor impurities actually introduces allowed energy levels in the band. And remember, in semiconductor terminology, these levels are called shallow levels because they are close to the energy edge, close to the band edge. These are called shallow levels. That is originally, right? Shallowly. So these are shallow levels, very close to the band, very close to the band, right? So this is the situation in donor and acceptor impurities, right? If you have, look, you can have a, a 3-5 semiconductor too, right? For this situation, for donor impurities, we will have number of electrons greater than the number of holes. And not will be greater than 3 naught. Because we have donor electrons. Holes are smaller. Holes are only the result of the energy provided, right, by the jumping of an electron from the valence band up to the conduction band, and then a hole will be produced. Here, if we have donor impurities, a hole is not produced. If we have donor impurities, a hole is not produced. Therefore, N naught will be greater than P naught. And for this, P naught will be greater than N naught. The number of the concentration of holes, if you have a third group impurity in silicon, then the conductivity will be mostly because of holes. Holes की वजह से आपकी सारी conductivity होगी. And if you have, this is called, this is called an N-type semiconductor. N-type semiconductor. Right? And this is called a P-type semiconductor. N-type, the conductivity because of electrons. P-type, the conductivity because of holes. Conductivity is why holes की वजह से होगी. Because you have introduced, suppose, a group 3 element into group 4. Right? For example, you say, आपने इसको गैलियम आपने इसमें into silicon. Silicon में आपने गैलियम introduce किया. Now, now, suppose you have a 3-5 semiconductor, right? 3-5 semiconductor. गैलियम आर्सेनाइड एक ग्रुप 3 का एलिमेंट है और एक ग्रुप 5 का. They are also semiconductor. For example, gallium arsenide. They are also semiconductor. So in this situation, right, if you put a group 2 and it replaces a group 3 element, then it will be an acceptor impurity, right? Acceptor. On the other hand, right, if you put a group 6 element and replace it group 5, so then you will have a donor, right? You can put silicon in it. You can put an element from group 4 into the 3,5. So if silicon replaces this, it will be a donor impurity. If silicon replaces this, it will be an acceptor. So these are the impurities, the role of impurities in semiconductors, and they are very important. Impurities in semiconductors are वेरी इंपॉर्टेंट. ये गन जो आप डालते हैं ये हमारे लिए बहुत फायदेमंद है. ये जो गन आप खालिश सिलिकॉन में जो गन डालते हैं ये हमारे लिए बहुत फायदेमंद है. We can control the conductivity of semiconductor by putting this dirt into it, right? Now we want to find the equilibrium concentration of electrons and holes without applying any field, without any temperature gradient. There is no temperature gradient, which means that this point of the semiconductor is hotter and that is colder. When one point of the semiconductor is hot, the other is cold, it means there's a gradient of temperature. So in equilibrium, no gradient of temperature and no gradient of potential, which means an electric field. So this is semiconductor will be in equilibrium. So now we want to see what is the situation of an intrinsic semiconductor in equilibrium, right? So equilibrium distribution of the equilibrium concentration, right? Of E electrons and holes in extrinsic semiconductor, right? We have an extrinsic semiconductor, right? So we said that the Fermi energy, right, gives you an estimate of where the probability of a level will be half, right? So if you introduce more and more electrons or donors impurities in a semiconductor, what happens? That the Fermi energy will go up. आप electrons में free donor states, donor impurities, you add it, and the Fermi energy will go up, right? So if M naught is greater than P naught, right? Then EF, the Fermi energy in this situation, will be greater than EFI. EFI intrinsic matter, right? So the Fermi energy will be higher than that, the level of the Fermi. And if P naught is greater than N naught, right? Then EF will be smaller than EFI, right? And if we say that the Fermi energy in the middle of the gap, so you put acceptor impurities, the Fermi energy level will come down, 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 right? So let us find the equilibrium concentration of holes and electron in the situation of, right, when the semiconductor is extrinsic. You have put some donor impurities, or you have put some acceptor impurities into it, right? So let us find out that. We know that from the intrinsic situation, the equilibrium concentration of electron was equal to Nc e to the power minus Ec minus Ef over kT. Right? That was the equilibrium distribution of electron. And now Moles was equal to Nv e to the power minus Ef minus Ev divided by kT. Right? Suppose this is the equation work. And that is 2. Right? Now, I am introducing EFI into it. Right? This EFI. Introduce into them EFI. So here, let me add and subtract EFI. So that if this is Fermi energy, so then I can see the difference of the intrinsic से खालिस से ये कितना ऊपर चला गया, खालिस से ये कितना नीचे आ गया. How much it has deviated from the intrinsic situation. So N naught, for example, donors. In case of donors, right? N naught will be equal to N C e to the power minus EC minus EFI and plus EFI. When इसको subtract किया, add किया, does not make any difference. And minus EF on H. Right? Ultimately, करके and naught is equal to NC, right? Is equal to NC into E, right? Now I separate them, right? I can separate the two. So is equal to minus EC minus EFI over KP and E, right? EF minus EFI. And this thing was equal to Ni, the intrinsic carrier concentration. So N naught is equal to Ni e to the power Ef minus EFI divided by AC. So look, now the equilibrium carrier concentration in the case of extrinsic semiconductor is equal to Ni. So N naught is equal to Ni if EF and EFI are the same. Right? So if that is equal to 0, and we'll put this. Now, The more the Fermi level goes above the intrinsic Fermi level, the concentration of electron increases. So we have derived an equation which will tell you how the concentration of electron changes with the motion of the Fermi energy up and above the band gap. If this difference is higher, then concentration of electron is higher. So it's also a function of T, right? So that is a situation for the extrinsic electrons. Similarly, right? For holes is equal to N I, right? E to the power minus minus E N I, right? Or KT. Right? Now, there is one difference. There is one difference, right? No minus is minus. So this gap increases, it will decrease. This gap increases, it will increase. Here's the minus sign, it's no minus sign. Otherwise, they are the same, right? So that is the extrinsic situation. Extrinsic concentration of holes in the valence band, concentration of electrons in the conduction band, right? Okay. Now let us see what is the product, right? Here goes the product guy. M naught or P naught to observe, you multiply the two electron concentrations and hole concentration in extrinsic situation. आपने डाल दिए हैं, you have put impurities in. Right? So what is the product? What is the product, right? The product. The This is important. The N naught P naught product. The N naught P naught product. So N naught P naught is equal to, you multiply these two. Multiply these two equations with each other, right? So you will get NC and V, right? E to the power, right? Minus, should I write it all? Okay, you can do that. Minus EV over KT, EMPF goals, right? And I go to that older equation. And I was a replacement for NC e to the power minus EC minus EF divided by KT. Similarly, this was this was different, right? So go back to that. Put NC and NE we introduced there. इससे पहले जो इक्वेशन था हमारा ये, इससे पहले ये NC है. Similarly, इसमें भी एक NV है, जो पहले हमने किए है. We have done it. So you combine them, you get this thing. And NC and NV, और ये क्या चीज है? ये क्या चीज है? EC minus EV. That is EC band gap. That is the band gap EG. right? So that is this thing, and multiply with E G minus E G or H e to the power. This is the multiplication. Okay, let me write it again. NC and V e to the power minus EG or KT and not P naught. Remember, it is now extrinsic. आप जितना भी चाहे मर्जी, जितना मर्जी you just increase the donor impurities, you increase the concentration impurities. Sorry, the acceptors impurities. There will be no change in this product. It is a very beautiful equation. The product always remains the same. No matter what is the number of donors, what is the number of, what is the concentration of acceptors. This N naught, P naught always remains the same. It is a function of NC and V and the temperature and the band gap energy. It does not say anything about the donor impurities or the acceptor impurities. So this is an important equation. We can use it later on. We should keep this in mind. हमारे पास ये एक tool है. So that we should keep this in mind. We can use it in different situations in calculating different things for this. And further, right? M naught and P naught, right? Here will be equal to this. When you go here, this was equal to Ni. Ni here, Ni here. Remember, you multiply N naught with P naught, multiply N naught with P naught. This will go with this. Only you get Ni square. So this is also equal to Ni square. So what we get? Gravitation 4, 3 and 4, right? From also from 3 and 4, N naught, P naught is equal to Ni square. And the constant, Ni intrinsic carrier concentration. इसमें कोई impurity का जिक्र नहीं. Right? So, these two equations are very important. We will use them, right? Now, in extrinsic situation, we say, right? The conductivity is because of two types of carriers, hole or electrons, right? So the number of holes is not equal to the number of electrons in this situation. Either the number of electrons will be greater, or which is n type, or the number of holes will be greater, which will be a p-type semiconductor. So if the number of electrons is greater, we say the majority carriers or electrons, n-type. We say the majority carriers are electrons and minority carriers are holes. Well, in n-type semiconductor, majority carriers are electrons, minority carriers are holes. P-type semiconductors, majority carriers are holes, minority carriers are right. So uh, we should stop here, and there is a little bit. I will just give you a brief introduction about the degeneracy and the non-degeneracy. Right? If the concentration of the impurity, right, is small, then they do not interact with each other. That is called non-degenerate semiconductor. When the impurities are not that much, up impurity, delta giant, then what will happen? That the number of impurities will become very much high, and that will make the semiconductor is degenerate semiconductor, because when they will be getting closer, more energy levels will be introduced, and that will make two states for the same energy level, suppose. So we call them degenerate semiconductor, right? And then for degenerate semiconductor, the Fermi energy will go to the conduction band. और degenerate semiconductor will आप बहुत ज्यादा डालते जाएं impurities ऐड करते जाएं so the Fermi level will go higher and higher and higher, and it will enter the conduction. Similarly, holes keep the acceptor will increase the acceptor impurities concentration, then the Fermi level will become smaller than the balance band energy, right? Okay, if you have any question, you can ask, and let me uh, take your attendance.